Hello everyone, my name is Carlota Bozal-Ginesta. I am a PhD student with Professor James Dowran at Imperial College London, and I'm going to talk about two molecular catalysts immobilized on TiO2, one for proton reduction into hydrogen, which I will mostly focus on, and the second one for CO2 reduction, which I have investigated for comparison. So I'm going to show and explain time-resolved spectroelectrochemical experiments from microseconds to seconds, which we have used to investigate charge transfer to the catalysts as a function of the oxidation state of the catalysts and the Fermi level of TiO2. Some of the most widely studied reactions for solar fuels production, such as CO2 reduction or proton reduction, are multi-redox reactions which require more than one charge to be brought together in a small spot. And this is energetically expensive because of the electrostatic repulsions. So the role of the catalyst, which is usually located at the surface of the electrodes in a photoelectrochemical cell, the role of the catalyst is to facilitate the interaction between the charges and the substrates by optimizing the energy of the intermediates and the energy barriers, ideally without degrading. But even in the presence of a catalyst, the intermediates that are most likely hindering multi-redox reactions are multi-reduced and multi-oxidized intermediates, because they tend to be quite unstable, and in particular in photoelectrochemical cells they can easily react with charges of the opposite sign that are nearby. So in this work what we try to do is to better understand the behavior of multi-reduced intermediates in molecular catalysts. So molecular catalyst is a small group of catalytic materials for solar fuels production. They are organometallic complexes based on one or a few metal atoms surrounded by a set of coordinated ligands similar to the active site of enzymes. Their major quality is that they can reach high turnover frequencies at low overpotentials, almost as good as natural enzymes and better than most inorganic materials. Also, their reactivity and selectivity can easily be tuned by modifying the ligands around the metal center. And finally, the major drawback is their stability. They last for a few hours. So in the last years, there's been many examples of molecular catalysts being immobilized on different substrates, such as metal oxides, carbon nanotubes, and metal organic frameworks. And this is a nice way to combine the good qualities of molecular catalysts with an enhanced charge separation and transfer to the catalyst. So here we investigated two molecular catalysts separately on TiO2, on 4 micrometer thick mesoporous TiO2. We then excited the bandgap of TiO2 at 355 nanometers. We scavenged the holes in the valence band with 3-ethanolamine, which worked here as an irreversible sacrificial electron donor, and we followed the electrons in the conduction band moving to the catalyst at the surface. We worked in acetonitrile so as to facilitate the accumulation and detection of multi-reduced species of the catalyst. We worked with these two molecular catalysts, COP2 for proton reduction and COTERPI for CO2 reduction. They are both catalysts based on cobalt. In both cases, the starting state is cobalt-3, and in both cases, the cobalt-3 needs to be reduced at least 2 times before catalysis can move on. In our group previously, COP2 was investigated in water, and from these results, the first electron transfer was determined to be faster than microseconds. However, in that case, we investigated the optical signal of the charges on TiO2. But here, because we want to distinguish between sequential electron transfers, we will focus on the optical signal of the catalyst and of the catalyst intermediates. So the natural step from here was to characterize the different intermediate states of COP2, cobalt-3, cobalt-2, and cobalt-1. So we did a cyclic voltammetry on ITO, which is transparent in the UV-Vis, and we assigned the 2 redox waves that we observed to the 2 redox processes of COP2. Then we applied a constant potential before and after the 2 redox waves, and we measured the absorption, which we assigned to cobalt-3 below 400 nanometers, cobalt-2 at 460, and to cobalt-1 and multi-reduced species, which have a characteristic absorption between 600 nanometers and 700 nanometers. So these absorptions correspond very nicely to the predictions from the FT calculations, which are shown here in gray. From now on, I will call for simplicity cobalt-2, cobalt-R, and cobalt-1 and other multi-reduced species as cobalt-RR. Before moving on to time-resolved absorption results, I have rearranged the spectroelectrochemical results here so as to simplify the interpretation later. This orange signal is the difference in absorption between cobalt-3 and cobalt-R, and this dark blue signal is the difference in absorption between cobalt-R and cobalt-RR. So what happens when we excite TiO2 in the presence of triethanolamine, the sacrificial donor, an intraband gap bias, and the catalyst at the surface of TiO2? What happens is that we see this signal between 600 and 700 nanometers raise. It peaks at around 10 milliseconds and then it decays within 1 second. This signal is very similar to this dark blue spectroelectrochemical signal, and they overlap very nicely. This dark blue signal is the same as this one, but this one is on ITO, and this one is on TiO2. And what this tells us is that what's happening here is that cobalt-R is being reduced to cobalt-RR. And it means that the catalyst, which initial state is cobalt-3, is very quickly reduced to cobalt-R, and cobalt-R remains at the surface in the dark. Then, upon excitation, what happens is that the photoexcited electrons reduce cobalt-R to cobalt-RR. Then cobalt-RR, within 1 second, reoxidizes back to cobalt-R by transferring electrons back to the conduction band of TiO2 or by transferring electrons to the electrolyte. We did these same experiments in the presence of water, and we saw the same signal but decaying faster, which we took as a sign that these cobalt-RR species are active in water and can react with protons to evolve hydrogen. So we have now identified the 700 nanometer signal, which here is represented over time. We have identified this as the reduction of cobalt-R, which is accumulated at the surface, into cobalt-RR. So we then moved on to vary the excitation light intensity so as to modify the concentration of excited electrons in the conduction band of TiO2. And what happened? What happened is that the dynamics changed completely, and the band at 600, 700 nanometers that we observe between microseconds and 1 second becomes completely flat, very similar to that of TiO2. Also, the kinetics very similar to electrons on TiO2. So what this is telling us is that the photoexcited electrons can no longer reduce cobalt-R to cobalt-RR and are probably relaxing and being trapped in low-lying energy states in TiO2. This drastic change occurred within a few hundreds of microjoules, which means that this double reduction of cobalt-R to cobalt-RR is very sensitive to the occupation of trap states in TiO2 and to the Fermi level of TiO2. To confirm that, we electrochemically filled up those states by applying a negative potential at around minus 0.6 volts versus NanoGe. And we could confirm what I just hypothesized by recovering the signal at 700 nanometers. So we have seen that the formation of multi-reduced species depends on the relative position of their redox potential with respect to the Fermi level of TiO2. So to further confirm that, we tried a second molecular catalyst, a CO2 reduction catalyst, which has 2 redox potentials at more negative potentials than the catalyst COP2. We tried this catalyst on TiO2 in the same way as COP2, in the same conditions, and we measured the transient absorption after exciting TiO2. And what we observe is the formation of cobalt-RR from cobalt-3. So there are 2 sequential electron transfers occurring here, and then cobalt-RR reoxidizes back to cobalt-3 within 1 second. So this means that in the case of cobalt, of coterpy, of the catalyst coterpy, there is no reduced species accumulating at the surface in the dark. So upon excitation, cobalt-3 can be reduced 2 times, but then it recombines or transfers electrons back to the conduction band of TiO2. So to summarize, We have seen that the formation of multi-reduced species called RR is quite slow. It takes place from hundreds of microseconds to milliseconds, and these species called RR are quite long-lived. We then see that co-RR species are only being obtained upon irradiation when there is enough electron accumulation in TiO2 conduction band. So it only happens at high enough light excitation intensities and low enough biases. As expected, we have seen that reduced species are prone to degrade and to recombine with valence band holes and conduction band states. And finally, compared to the catalyst COP2, we saw that the catalyst, the CO2 reduction catalyst coterpy, that did not accumulate, the reduced species did not accumulate in the dark. So to finalize, I would like to thank all the people that contributed to this work, in particular in James's Dowran group and also in our collaborator Erwin Reisner's group at the University of Cambridge. And I would also like to thank you all for your attention.